6.2 is characteristics of the equations of polynomial functions. So what we want to do in this section here is we're going to make a connection between the coefficients and the constants in an equation of a function and the characteristics of the graph of the function. So what do the coefficients and the constant tell you so that you can graph the equation? So in standard form, a polynomial function is written so that the powers of x are in descending order. So they always go from the highest power to the lowest power. So standard form then for the different, there are three different equations that we're looking at. So linear would be f of x is equal to ax plus b, and a can't be equal to 0. For standard form, for a quadratic, you have f of x is equal to ax squared plus bx plus c. And for a cubic, you have, f of x is equal to ax cubed plus bx squared plus cx plus d. And for each one of these, your a can't be equal to 0, because if our a was equal to 0 there, then that would get rid of our x squared. So then we'd just be at bx plus c, which would be a linear function, so it would no longer be a quadratic. So your leading coefficient then is the coefficient of the term with the highest power. So in the cases that we have above here in the standard form, that would mean our a value. So in standard form, it is a. So your constant then is just the term without the x variable. So example, if you had f of x is equal to 2x cubed plus x plus 1, your leading coefficient, leading coefficient is equal to 2, and your constant would be positive 1. If I had f of x is equal to 3x cubed plus 4x plus 0, my leading coefficient would be 3, and my constant would be 0. So linear polynomials, just taking a look at a couple examples here. If we had fx is equal to 3/4 x minus 2, if we take a look at this, our degree is 1. Our number of x-intercepts that we would have, because it's linear, it's only going to be 1. Our y-intercept would occur at, in this case, negative 2, because that is our b value. Our domain for this one is a set of values for x such that x is an element of real numbers, because you can substitute anything into it. Our range then, set of values for y, such y is an element of real numbers. So I'm just going to pause here and go up and draw this one for you. So fx is equal to 3x minus 2. So my y-intercept was at negative 2, so I go down 2. My slope was equal to 3/4, so that means I go up 1, 2, 3, and over 4. 1, 2, 3, 4. Now I draw my line from there. Just going to slide it over a little so it's actually lined up. And there you have your linear function. So now number of turning points. This graph, because it's linear, continued in one direction, did not have to change any directions. It didn't go up, it didn't go down, it just went in a continuous line. Sorry, I'm just finding my spot here. End behavior. So remember, end behavior, we always start from the left to the right. So this end behavior, it would start in quadrant 3 and end, oops, that should be an arrow in between there, and end in quadrant 1. Okay, next example. Fx is equal to negative 2x plus 6. So my y-intercept, or b value, is at 6. My slope is at negative 2. So 6, 1, 2, 3, 4, 5, 6. Slope of negative 2, so that's the same as saying negative 2 over 1. So I go down 1, 2, and over 1. So if I connect my dots, actually that's pretty close. So now to fill in my information, my degree for this, it was linear, so it was 1. Number of x-intercepts, crossed it in one spot. My y-intercept was at, whoops, 6. My domain, because it's a line, it's all real numbers, as is the range. Number of turning points, there were none. Now this graph going from left to right for our end behavior started in quadrant 2 and ends in quadrant 4. So even though I didn't continue my line down much further, you can tell that that's where it would be done. Oh, that's nice. I don't know why that one pasted in there sideways. Okay, I'm just going to pause here and fix that. Okay, so quadratic polynomials. If we want to draw this one here, if we take a look at this, we know our a is equal to, 1/2, and our c value, our constant, is 5. So that means if our constant is 5, then that means that your x or your y-intercept is going to occur at that value, because to find y-intercept, you let x equal 0. So I'd have 0 squared, which is 0, so that's going to get rid of my 0.5. 2 times 0 is 0. So your y-intercept is at 5. So you know your graph is going to be crossing at 1, 2, 3, 4, 5. So we know from quadratics from grade 11, and if you were in pre-calc last year, or last semester, when you have a quadratic function, you look at your a value. So my a value for this one is positive, and it's 0.5 or a half. So I know my graph is going to be going up because that a is positive. And if you remember when we were doing our graphing of the polynomials, we did first you did over 1 up a squared over, or 1 times a squared, and then you did over 2, and then you went over, or you went up 4. And then you went, you went over 3, and then you went up 9, because you always square it. If there's an a value, then you multiply it to that. So because our a is 1/2, so our normal is over 1 up a times 1 squared. And then you went over 2 up a times 2 squared, and then over 3 up a times 3 squared. So if a is a 1, then it's just over 1 up 1, over 2 up 4, over 3 up 9. So because my a is a 1/2 here, that means that I'm going to be going over and up a half every time. So it'll be over 1 up 1/2, over 2 up 1/2 times 4, so that's 2, over 3 up 1/2 times 9, so that's 4.5. You need to find your x-intercept in order or not your x-intercept, your vertex in order to do this. So this is where you just put this in your graphing calculator. You could find it using your PQ formula. So P is equal to negative B over A, and your Q is equal to C minus AP all squared. So you could substitute your B and A values and find your P. So in this case, it would be 2 divided by, I can write it down, I guess that'll, so my P would be negative 2 over 2 times 1/2, so that's just over 1, so my P is equal to negative 1. Your Q then, I should have left more room at the top. Oh, but I probably have more room at the bottom, don't I? Oh yeah. So if my P is equal to negative 1, what did I say? No, I said negative 2, didn't I? Yeah, because it's negative 2 divided by 1. So my Q is equal to C minus AP squared. So Q is equal to, your C was a 5, minus 1/2 times 2 squared. 2 squared is 4. 4 times 1/2 is 2. So it's at 3. So that would mean your vertex for this one is at negative 2 and 3. So negative 2, 1, 2, 3 puts me right there. So then doing my over and ups, I go over 1 up a half, over 1 up a half, over 2, and it should be 4, but I have to divide that by 2, so over 2 up 2, so that gives me my x-intercept or y-intercept there, and then over 3, and it should be up 9, but it's 4.5 because I have to divide by 2, so 1, 2, 3, 4.5. So this is what my graph looks like. So that's a really brief refresher of graphing. The other way to have done this is pull up your graphing calculator. Go into your y equals. Ooh, look at this, has fancy colors. And just put in your 0.5 x squared plus 2x plus 5. Hit your graph. Have to adjust your window a little bit. Oh, hey, this is the new version, the silver edition. It gives it to you in color. So based on that, then you can do some calculations. You could bring up your table if you wanted to. So if I go into second table, here it'll just give you some of the values that you can plug in. So if you take a look here, when, oh, these only went to 0. So let's change this. Will it let me? Can I go higher? Oh yeah, there. So when I look at some of my negatives here, I go -6 is 11, so I've got 2 at 11. -5, 7.5, 1 is at 7.5. So then I can see where my repeat happened. So at -2, 3 right here, that was where the vertex was. When x equaled 0, y was equal to 5. So just off of the table function, without doing any of the trace or the calc, well, I guess it's second trace, which gives you the calc, and then you do to find the x-intercepts and things, or y-intercepts, you could do it that way. This is just a little bit simpler. Okay, so based on my graph here, my degree was 2, number of x-intercepts, because this graph is above the line and it is going up, I have 0. My x domain for my x's, I can go positives and negatives, doesn't really matter. So my domain is all real numbers. Your range then depends on whether your graph is a maximum or minimum. So this graph has a minimum point, so that means for my y, it's going to be everything greater than or equal to whatever my q value was, or whatever my maximum or minimum value was. So that was here at 3. And y is also an element of real numbers. Number of turning points for this graph, there was 1. My graph was going down, and then it hit the vertex and started to go back up. So the end behavior for this one, going left to right, it started in quadrant 2 and ended up in quadrant 1. Okay, -x squared plus 6x minus 9. So my constant is a -9, so I know that's what my y-intercept's going to be. I know my degree for this is a 2. So what else can I find out from this? Well, if you wanted to do the steps, you can find your p and q to get excuse me, to get your vertex, and then from there you could do your over 1 down 1 over 2 down 4, because remember this is a negative, so that means my graph has to go down. But instead we're just going to plug this into our graph. So we're looking at negative, and make sure you use the negative and not the minus. X squared plus 6x and I'm going to change this, because if I do yeah, I want this one to be a +9, so make sure or no, sorry, -9. It's okay. -9. Hit your graph. So you can see once it gets on here. There we go, that's what your graph looks like. So you can kind of look, right from looking at this, you can see where your vertex is going to be at 3, 0. But you can check on the table just to make sure, and then also to plot your points. But if I look on my table, my vertex 3, 0, if I move down here a little bit, there, you can see my numbers are repeating. So 3, 0, and then I had -1, -1, -4, -4, -9, -9. Okay, so when x equaled 0, my y was equal to -9, so that worked with that value there. So my vertex was at 3, 0. My y-intercept was at -9. And you could look off of the table if you want to pick out some of your other points, but it's just as easy from here just to do your over 1 up, or over 1 down 1, over 2 down 4. And then I know it was at 3 and 9. Oops, that kind of missed the mark there. That's even worse. You get the idea. So number of x-intercepts, this one had 1. It was exactly on the x-axis. My domain, again, my graph can go either way. My range, though, for this one, because my graph is going down, I'm going to have a maximum, so that means my y has to be less than or equal to that maximum value. And my maximum y value was a 0. And again, y is an element of real numbers. Number of turning points was 1. End behavior, this graph would have started in quadrant 3 and ended in quadrant 4. So even though in my graph here I haven't drawn it very well, you can see that it would continue to go in that direction. I'm not sure why that blue line is there, but it's alright. Okay, so last graph. fx is equal to negative 2x squared minus 3. So I know my degree is 2. I know I have a y-intercept at negative 3 because of that constant. So now let's graph it and see what it looks like. So it's going to be x squared minus 2x minus 3. Oops, I missed one here. Yep. Thought I would save time and it didn't. Minus 2x minus, whoops, not minus. Delete that. You have to watch. It has to be a negative 3 because it's an operation. In the other equation in front of the x squared, it's giving you a positive or a negative, so it's telling you the sign, but in between the terms it's an operation, so you have to use the minus sign, not the negative. Okay, so let's graph this. So this graph is going up. I can see it crossed at negative 3, and I can pick a couple of points here. We're at 3, 0, and negative 1, 0. If I look on my table, I have negative 1, 0, 3, 0, 0, negative 3 was my, or no, sorry, where's my 1, negative 4 is the vertex. So 1, negative 4, oops, that's 2. Here's 1, negative 4. My vertex, or my y was there. I had a point there, and then a point here. So, and then I would also have a point there. So I could draw my graph. And there you have it. So number of x-intercepts, this one crossed twice. My domain, again, I can use any x value that I wanted. My range, because my graph is going up, so that means I'm going to have a minimum. So it has to be greater than or equal to my y value at negative 4, I guess my q value. Number of turning points, 1. End behavior, started in quadrant 2 and ended in quadrant 1. So the next page is for cubic polynomials. So fx is equal to x cubed. So my degree for this is going to be 3. I don't know my x, well you might know your x, number of x-intercepts, but we'll wait till we do the graph. Your y-intercept, because this is like x cubed plus 0, your constant would be 0, so my y-intercept is going to be at 0. So if I put this into my calculator, y is equal to x, and use a little caret, cubed. Hit your graph. So the graph looks like that. So it's like a half of a polynomial, or half of a quadratic on one side, and then half on the exact opposite corner of it, or exact opposite quadrant from it. So if I look at my table, my values, I don't have a vertex for this per se, but I have that point 0, 0, which I can't draw it just yet. And then if I look, I'm going -1, -1, and then it goes 1, 1, 2, 8, -2, -8. So whatever was positive will stay. If my x was positive, then my y is positive, but if my x was the negative, then my y is the negative. So if I want to graph that then, so I was at 0, 0, 1 and 1, and then it was -1 and -1. If I put in a 2, it's going to be at 2 and 8, and then 2 and -8. And that's sufficient to draw for now. So my graph would go like that, and it would go like that. So number of x-intercepts was 1. Your domain, I can use any x value that I want. My range, again, I can go all the way up and all the way down, so it's going to be all real numbers. Number of turning points was 0, because this graph continued to go from up, and it curved. It didn't change direction though. It didn't go in another direction. It didn't go back down anywhere. So this one has 0 turning points. And my end behavior, this one started in quadrant 3 and will end in quadrant 1. There we go. Okay, so my next equation. We got negative x cubed. Well, have to make sure you move over. Plus 2x squared plus 4x minus 8. So just looking at that, I know I should have a y-intercept at 8. So my degree is 3. Let's graph it. Oh, where did I make a mistake? Oh, negative. So I graph it, and it looks like that. So my degree for this one is 3. I have an two x-intercepts. It crosses here, and it touches there. So it crosses at -2, and it touches at +2. So based on that information, I can start to, I'll plot a couple of these points. So I was at 2 and 0, and I had another one at, or my y-intercept was at -8, so 1, 2, 3 is right there. The other spot that it crossed was here at 2, 0. And there was another value. Pick another value there. So 3 and -5. 3. There. So my graph did this, came down, went there, touched, and then came back down. So my degree for this is 3. Number of x-intercepts was 2. Y-intercept was at -8. My domain, again, I could go as far as I want on the x's. My range, however, though, my graph goes up forever, and it goes down forever. So even though I have these two turning points here and here, my graph still keeps going. So it's also real numbers. Number of turning points for this one. My graph changed direction here at 0, -8. I was going down, and then at that point it went back up, and then it changed directions again here at 2, 0, because the graph went back down. So the end behavior for this one, my graph started in quadrant 2, and it ended, excuse me, in quadrant 4. So last graph. I've got a degree of 3. I know for sure. I know my y-intercept, or sorry, my x-intercept is going to be at 0, -4. So now let's graph it and see what we can find out. So x cubed plus four x squared minus x minus 4, right? X cubed plus 4x squared minus x minus 4. Okay, so if I graph it, it's doing a little bit of that. So if I look off of here, I can see I've got an x-intercept at 4, 0, or -4, 0, at -1, 0, and then again at 1, 0. My y-intercept was at -4. So let's plot those. I'll just put these on there, and then I'll nope. There's the one that says leave this out front. Oh, there we go. Always in front. Okay, so my table. So x-intercepts, we're at -1, 0. And then there was one at 1, 0. And then I have to move up this way. So I can see the next one was, whoops, now I'm going crazy. Was that -4, 0. Why does this one look like it's saying X? Oh, that's an 8. Okay, I couldn't tell from there. Okay, so -4, 0. At -3, it was at 8. We could do that one. And then we knew we had a y-intercept here at -4. What other positive one? Is there one that works out nicely at 2 and 10? So we can draw that one too. 2 and 10 will be right up at the top. Okay, so my graph was going like this. So number of x-intercepts, there were 3 for this one. Domain, again, I can use all of my x values. And my range is the same thing. Number of turning points, so my graph was going up, and then it turned and went down, so that's one turning point, and then it hit the y-intercept, and then it turned and went back up, so it had 2 turning points. It started in quadrant 3, and ends in quadrant 1. Okay, so just a little refresher, reminder, review. So the key ideas when a polynomial function is in standard form, the maximum number of x-intercepts the graph may have is equal to the degree of the function. So if I have a degree of 2, then the most x-intercepts I can have is 2. I'll never have 3. So the maximum number of turning points a graph may have is equal to one less than the degree of the function. So when I had a degree 2, the most turning points I could have was 1. When I had a degree of 3, the most turning points I could have was 2. So I never did have one that had 3 turning points. The degree and the leading coefficients of the polynomial function indicate the end behavior of the graph of the function. So if I had a degree of 2 and my leading coefficient was positive, then my graph is going to be going up. So it'll be a quadrant, start at quadrant 1 and a quadrant 2. If it was leading coefficient was negative for a quadratic, so degree of 2, then it would be going down, so then I would be starting in quadrant 3, ending in quadrant 4. For the degrees of 3, for a positive, if I didn't have a constant, I was starting in quadrant 3 and ending in quadrant 1. If it would be a negative degree of 3 without a constant, I would be starting in 2, ending in 4. For a positive cubic, I would start in quadrant 3 and end in quadrant 1. For a negative cubic function, I would start in 2 and end in 4. So it says a constant term in the equation of a polynomial function is your y-intercept on the graph. Okay, and I think there should be good. So this just is kind of a recap of what was there. So linear and cubic polynomial functions have similar end behaviors. So for our degree, if we look at this one, our degree is odd, so 0 or 1. Sorry, not 0 or 1, 1 or 3. Our leading coefficient is positive. Okay, this is a positive 1/2, this was a positive 1/2. Then I started in quadrant 3, ended in quadrant 1. If my degree is odd and the leading coefficient is negative, then it was just the opposite. I start in quadrant 2 and end in quadrant 4. Just repeating what I said in the last one, but putting it in a chart. So for one's quadratic polynomial functions have different end behaviors than linear and cubic. So we're looking at a degree of 2. Leading coefficient is positive. The end behavior is going from quadrant 2 to quadrant 1. If our degree is 2, leading coefficient is negative, then we're going from quadrant 3 to quadrant 4. So when you're doing these, if you want to do the calculations to find your P and Q for the quadratic ones, you can go ahead. Otherwise, put them into your calculators, hit that table function, and then pick out your main values. So your x-intercepts, your y-intercepts, and then just a couple other points that can easily be plotted, so something that is on an exact coordinate and not decimals.